We are now living amidst the global coronavirus pandemic, and in some parts of the world, they are now facing a second wave of the virus, where the number of cases just keep on climbing and the number of deaths caused by the coronavirus just keep on rising. We're concerned that there were no immediate actions taken during the onset of the pandemic, which leads us to our current situation. In nature, we notice fractals among us, and we wonder if we can use the fractal dimensions of these viruses in order to project its fatality rate. Hello, my name is Nicole.
Hello, my name is Kevin.
And today we're going to present our experiment, a quantitative fractal dimension model of virus nanostructure for fatality rate projection. The world is shaken by the COVID-19 pandemic. In the wake of the pandemic, early assessment of virus fatality is paramount, as any necessary action in order to mitigate the spread of the virus could be taken immediately. Complex proteins fold up and wrinkle around the surface of the virus, and the fractal dimension describes this roughness, ruggedness, jaggedness, and the complexity of the virus. Fractal dimensions could provide useful parameter in order to assess the fatality rate of the virus.
The objective of this research is to produce a mathematical model that would project the fatality rate of the virus by analyzing the fractal dimension of the virus nanostructure, and also to check the degree of the accuracy of the mathematical model in projecting the fatality rate of COVID-19. Therefore, our research questions are: is there any correlation between the fractal dimension of the surface structure of a virus between parameters such as radius, volume, surface area, and fatality rate of the virus? Second, how will the mathematical model be developed? Third, what is the degree of accuracy of the mathematical model in projecting fatality rate of COVID-19?
Unlike man-made objects, most natural objects are in fact not smooth-edged. The concept of fractal geometry allows irregular curves to have a non-integer dimension, and this is where fractal dimension comes in. Fractal dimension is an index measuring and characterizing the geometrical complexity of an object's fractal patterns. The higher the fractal dimension, the more complex an object is geometrically. And this fractal dimension can be measured using the box counting method, which is a method in gathering data by breaking down the dataset or image into smaller pieces in order to obtain its pixel count and its pixel size to obtain the fractal dimension. If fractal object X is divided in n number of objects similar to X in a homotety of 1 out of R, then the fractal dimension can be calculated as follows in this formula. Fractal dimension D equals to log n per log 1 out of R.
We have selected images from 6 different viruses from the family of Picornaviridae, which we have selected the images from a medical resource called FiberDB. Here is the summary of each virus's incubation period and also fatality rate. Those 6 different viruses images are taken using cryogenic electron microscope. Cryogenic electron microscope is a technique to take images with high resolution and provide a detailed structure of biological molecule structure. Case fatality ratios are calculated as follows. Allometric scaling law proposed by Ji-Hwan He from Dongguan University suggested that there is a correlation between the fractal dimension of the virus and also the fatality rate of the virus, which is shown as follows.
The images of the Picornaviridae viruses were binarized through Fractal for imagery software, and it yielded black and white images of the virus. These images will be processed through Fractal for imagery to gain measurements on its fractal dimensions along with its other parameters as shown in this table. Fractal dimension can be measured by plotting log n against log 1 out of R, and the slope of the linear regression will yield the fractal dimensions using the measured box counts. Log n will be plotted in the y-axis, while log 1 out of R will be plotted in the x-axis.
Graphs will be constructed to have a better visualization between the correlation of fractal dimension of the surface structure of virus and the volume, radius, and surface area of each virus. The mathematical model will be constructed using the multiple regression on 2 independent variables, which are the fractal dimension of surface structure of virus and the spike protein of a virus.
These are the results of the measured fractal dimensions of the virus surface nanostructure. As you can notice from the graph, the ecovirus has the lowest fractal dimension out of the 6 viruses, while the poliovirus has the highest fractal dimension out of the 6 viruses. And here you can see that as the surface area of the viruses increases, the fractal dimension increases as well. And these are the slopes of the linear regression that shows the fractal dimension of the viruses. So log n, which is the pixel count, is plotted on the y-axis, while log 1 out of r, which is the pixel size, is plotted along the x-axis. These two graphs shows the slopes with the ecovirus and the hepatitis A virus. These two shows the rhinovirus and the Coxsackie viruses, and this one shows the enterovirus and the poliovirus.
Those three graphs resulted from the correlation between the fractal dimension of nanostructure of a virus and the radius, volume, and surface area of a virus. Here are the results of the correlation coefficient between the fractal dimension nanostructure of a virus and radius, surface area, and volume, which we calculated using the Pearson correlation coefficient formula. The result shows that the correlation coefficient between the fractal dimension of a nanostructure of a virus and the surface area of a virus has the highest p-value, which means it has the most correlated. Here are the results of each fractal dimension of the spike protein of the virus. Here are the results of the graph from the correlation between the fractal dimension of the virus nanostructure and spike protein, and also the fatality rate of each virus.
Multiple linear regression can be used as a tool in constructing our mathematical model, which can be used to project the fatality rate of the virus. These are the results of the multiple regression, and the analysis of variance shows a p-value of 0.026, which is statistically significant as it indicates a strong evidence against the null hypothesis. The null hypothesis suggests no relation between two variables. So that being against the null hypothesis suggests a strong relation between the two variables, which is the fractal dimension of the virus surface structure and the fractal dimension of the virus spike protein. From there, we can construct our mathematical model as seen in this slide. Y is the virus fatality rate, x1 is the virus fractal dimension of the virus surface structure, and x2 is the fractal dimension of the virus spike protein. So we tried to test our mathematical model on projecting the COVID-19 fatality rate. To project the fatality rate of the COVID-19, cryo-EM images of COVID-19 surface structure and its spike protein were converted into binarized images and were evaluated using the Fractal for ImageJ software. So by obtaining the fractal dimension of the spike protein and the surface structure and inserting them to the mathematical model we constructed, it yielded a fatality rate of 7.76%. So we compared the fatality rate projected by our mathematical model to several sources that reported the fatality rates as shown in this table. So as of May 2020, during the onset of the pandemic, the fatality rate was reported to be about 6.7% globally, which leads to a degree of accuracy of 86.3%. But after people are starting to take action in order to mitigate the spread of the virus, the fatality rate globally dropped to 2.75% as of October 2020, which leads us to a degree of accuracy of 35.4%. So these fatality rates can differ in accordance to how well people might take action against the virus. So to conclude, the degree of accuracy can range from 35.4% to 88.7%.
Concepts of fractal geometry in the nanostructure of virus may be useful to determine the fatality rate of each virus. The degree of accuracy of the mathematical model gives a satisfactory projection with a range of 35.4% to 88.7%. The limitation of these features is that there is some uncertainty range of fatality rate of some virus, which the mathematical model could only provide a fixed projection of the fatality rate of a virus.
So for future work, it is suggested that a new mathematical model will be constructed specifically for the same family group, which is the Coronaviridae family, in order to project the fatality rate of the COVID-19 with higher accuracy. Benoit Mandelbrot once said that clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth. Nor does lightning travel in a straight line. So viruses are complex objects, and its complexity will determine its fatality. Thank you.